Okay, lads and ladies, welcome back to Calc 1. Today is another fun day in the land of differentiation. Last time, we got our first little sneak peek at the differentiation rules, the shortcuts that get you around having to work with that terrible limit definition of the derivative. I don't mean to disparage the thing. The limit definition of the derivative is not truly terrible, but it is clunky at best. So from a conceptual standpoint, that is by far the most useful way to think about the derivative. And if you're trying to understand what the derivative is or how you could get slopes of tangent lines, well, that limit definition is for sure the way to go. But the reality of the situation is we want to solve lots of problems and we want to solve them fast. So what we don't want to do is need that limit definition every damn time we go to calculate a derivative. We saw one example last time where we were able to differentiate a power function, even though the power wasn't an integer, using the power rule. And then we saw how we could use the two rules, the one that says you can split up derivatives and take the derivative of each little piece on its own, together with the power rule to differentiate a big polynomial or a big multinomial as long as each of the individual terms is a constant times a power function. So I'm going to turn on the screen share. We'll get rolling here. This is MAC2311, section number 004, which is a Calc 1 class. And the date today is the 26th of January, 2022. Today, we're going to do a little bit more with the power rule. We're going to introduce the, which is power rule, and I'll just leave it like that. We're going to talk about derivatives of exponential functions. And then we're going to introduce the product and quotient rules. Now, all of these sections here, all of this material from section 3.1, and all of this is 3. Well, the first two are 3.1, sorry. So these are both coming from section 3.1. And the third item is coming from section 3.2. All of these are fairly straightforward from like a lecture standpoint, right? It's very easy for me to just like write down the rule and say, okay, here it is, now you've got it. The big thing though is practice, right? Like actually implementing the rules requires a certain amount of finesse and a certain amount of practice to get comfy with it. So don't let my brevity give you the impression that this stuff is not a big deal. We will be using these rules constantly throughout the whole semester. You'll need them in every calc class you ever take. Let me just remind you what the power rule said. This said that if you want to take the derivative of x to the n, so x to the n all primed, that is n times x to the n minus 1. Or in Leibniz notation, you could say d dx of x to the n is n x to the n minus 1. That was our power rule. The other big theorem last time, and I'll use the same sort of notation here, said that if you have f plus g and you want to prime that whole thing, that this is f prime plus g prime. And if you have a constant times f that you want to differentiate, that is just the constant times f prime. And you could write both of those in the Leibniz notation as well. As d dx of f of x plus g of x equals df dx plus dg dx and ddx of c times f of x is c times df dx. And remember, there are some advantages to the Leibniz notation, as irritating as it may be. You can think of the numerator here as like a tiny little rise, and the denominator here is like a tiny little run. So what we're doing is we're talking about a rate of change, right? The Leibniz notation emphasizes the fact that these are rates of change. But these are the main results from last time. And you'll see me, I'll use the prime notation pretty much everywhere I can. It's just nicer. So these two things together allowed us to differentiate any polynomial. Just a quick recap. If f of x is x cubed plus 3x squared minus 2x plus 7, you can find f primed of x, and I will work this for you really quick, just as a reminder. The examples we did last time, I was very verbose, right? I wrote ddx in front of this thing, and then used this theorem to split those up. The way people do this in practice is just by looking at each piece and applying the power rule to each piece on its own. So you don't need to write out every little bit here with its own derivative. You can just write down the result. So the x cubed piece, if I apply the power rule, right, with n equal 3, would be 3 times x to the 3 minus 1, or 3x squared. The 3x squared piece, if I apply the power rule and the constant multiple rule, right, which says that the constant 3 will come along for the ride, I get 3 times 2x to the 1. And then I have minus, this one you might want to think about just a little bit. That would be 2 times 1x to the 0 when you apply that power rule, right? X is x to the 1. So if you look at this with n equal to 1, you get 1 times x to the 1 minus 1, or 1 times x to the 0. So the derivative of x is 1 times x to the 0, which is just going to be 1. And the derivative of a constant, you can think of that constant as x to the 0. The rule works here as well. That would be 0x to the negative 1, which is just 0. So a fun little note here associated just with that last piece, but the derivative of a constant on its own, not multiplying some power of x, but the derivative of a constant is always 0. So for any constant c, the derivative of c is 0. If you think about the graph of a constant function, like the graph y equals 7 on its own, it's a horizontal line. The slope of the tangent line to a horizontal line is always going to be 0, right? The slope of that line is always 0, no matter where you look, which means its derivative is always 0. So derivative of a constant is 0. You can think of it as a consequence of the power rule. That's one way to do it. Or you can think of it as its own thing. Either way is fine. So this is how most people would differentiate this, right? You just look at each piece on its own, and then you add them or subtract them according to whether they're added or subtracted in the original. And then we simplify a little bit. So this is 3x squared plus 6x, and then minus 2 times 1 times x to the 0 is just minus 2. And the general thing that you appear to see here, the derivative of a degree 3 polynomial being a degree 2 polynomial, is true. As a consequence of this power rule, that when you differentiate any polynomial, the degree, the largest power of x, all the powers of x, but in particular the largest power of x, will go down by 1. Okay, any quick questions on the power rule or the theorem from last time before we charge ahead? Questions on this stuff, the notation? I know this bullshit is like a little wonky. Any questions on the example here? Okay. The other functions that everybody likes to differentiate, besides polynomials and power functions, are exponential functions. Which in general look like this. This lives in section 3.1 because it's one of the other really nice differentiation rules. Unfortunately, I cannot give you the full story today. I can give you the most important part of it, but I cannot give you the full story. So functions of this form are exponential functions, right? And we know what their graphs look like. If b is bigger than 1, this is a growing exponential. It looks like e to the x. If b is less than 1, then this is a decaying exponential, right? Like 1/2 to the x. The trick, as with the power rule, is to start with the definition, the limit definition. Anytime we want to prove a rule, we have to go back to the definition. And if I plug in b to the x for that function, then f of x plus h would be b to the x plus h minus f of x is b to the x, and everybody is still divided by h. Unlike many of the other examples we've seen, this doesn't really look like one of those limits I gave you as a homework problem before. I mean, it has the same sort of shape, but the actual literal algebraic objects in here look different, and there's a reason for that. This limit is actually kind of hard. The way your textbook gets around this is deeply annoying. I will show it to you, and then I'll do my best to connect it to the definitions that you've seen in pre-calculus. But before we do any of the fancy stuff, I want to drive home one big point. There is an algebra rule for exponents that says if you take like number a and you raise it to a sum of 2 powers, that's the same as a to the first power times a to the second power. Usually this is learned somewhere around college algebra, and it's usually taught as the thing on the right is equal to the thing on the left. If you multiply like bases, that's the same as adding the exponents, right? That's how we usually learn this. But we're going to use it in the other direction to help us simplify this part. So according to that rule, my limit here becomes lim h to 0. B to the x plus h is b to the x times b to the h. And then I have still my minus b to the x, and everybody still divided by h. Why is this a nice thing to do? Well, if you look at that numerator, you have a binomial, right? Two terms separated by subtraction. And in the first term, you have a b to the x factor. And in the second term, you also have a b to the x factor, which means you can factor out b to the x. So I get b to the x times b to the h minus 1 over h. Your limit is a limit as h goes to 0. So as far as this limit is concerned, b to the x is a constant. This part right here doesn't have any h's in it. So this piece can come out past my limit, and I get b to the x times lim h to 0, b to the h minus 1 over h. And this is as far as I can take you in full generality. So in full generality, right, your totally general exponential function b to the x will have derivative equal to itself times this thing. And what the fuck is this thing? Let me just call it a constant. So this is b to the x times some constant c, where c is this constant. So every exponential function f of x equals b to the x has derivative f primed of x equals b to the x times some constant for some constant c. The necessary tools to calculate this limit are beyond the scope of this course for the moment. I will teach you one thing a little bit later that allows you to tackle this particular limit and other limits like it. But right now we don't have the things we need. There is no algebra trick that will let you factor out an h from this numerator to cancel with the h downstairs. Requires some heavier machinery. But I can tell you that that limit is a number. Right? That limit does exist. I can't prove that to you conveniently. It's not worth the time. But I will tell you this limit for any positive number b does indeed exist. And it just comes out to some constant. If you're dying to know, this constant is the natural log of b. That's actually what you get there. And I'll prove it to you eventually, right? Down the road, not right now. For now, what I want to do is what your textbook does. Say, in the special case, where b is equal to e, that is Euler's number, 2.71828, blah, 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 blah. we get, well, f of x, okay, that's e to the x. And f prime of x would be e to the x times the limit as h goes to 0 of e to the h minus 1 over h. So really quick, in summary, every exponential function has a derivative that includes the original function. The derivative of b to the x is always going to be b to the x times some constant. And that constant is limit h to 0, b to the h minus 1 over h. So differentiating exponential functions always returns the original function times some constant. And if you're looking specifically at the natural exponential function e to the x, then that looks like this. Here's where your book gets on my nerves. Anybody care to guess what your book does with this piece? Can anybody smell a whiff of bullshit coming through the window?
They get rid of that H under it?
Even worse, even more insulting. Yeah, Cameron's got it in chat. They just declare this to be 1. It is, because in general, this limit is the natural log of b and the natural log of e is 1. What your book does is they say, the number e is defined to be the unique number such that the limit as h goes to 0, e to the h minus 1 over h equals 1. Therefore, f primed of x is e to the x times that limit is just e to the x. And if this sounds like bullshit, boy, it is. This is like when on a test, you feel like you know what the answer is, so you just write the shit down and you never explain it. This is that. This is James Stewart doing exactly that. He's like, I know the derivative of e to the x should just be e to the x. So whatever this leftover bit of shit is here, I'm just gonna say it's got to be 1, because otherwise I won't get the answer that I think I should get. But it's terrible logic. It's correct. So we'll start there. They haven't told you a lie. The derivative of e to the x is e to the x, and this limit is 1. But this is not the definition of the number e that you saw in pre-calculus, or in college algebra, or anywhere else, or the definition of the number e that anyone on the fucking planet besides James Stewart in this textbook uses, because it's a ridiculous definition. I can show you the connection between the normal definition of the number e and this alternate definition of the number e. I don't want to burn too much class time on it. So before I do that, let me just say the result is what you think it is. Theorem. E to the x is its own derivative. If f of x equals e to the x, then f primed of x equals e to the x. That is, and the kind of alternate notations, right? E to the x, all primed is e to the x, or d dx of e to the x is e to the x, whatever language you want to use to describe this fact, e to the x is its own derivative. When you differentiate the natural exponential function, you get it back. And this is why all of your algebra teachers are so hard for e to the x, because it's an awesome function with respect to the calculus operator. It is a fixed point of the differential operator d dx. It's the only function in the world that does this. And that's why the number e is so special.
So do you want us to know what the book says?
Nah.
No, okay, sweet.
I need you to know this. This is what I need you to know, that e to the x is its own derivative. Now, I do think it's healthy in an inquiring mind to understand where a statement like this comes from, because this is at the heart of the matter. So why is e to the x its own derivative? The proof can be broken down into two parts, one of which we've already done. Right, that the derivative of e to the x, if f of x is e to the x, then we know already, we've shown that the derivative is e to the x times this wonky limit, e to the h minus 1 over h. So we need to show, so it suffices to show that the limit as h goes to 0 of e to the h minus 1 over h really is 1. And the trick, the normal definition of e if you've seen one anywhere, it's this, it's the limit as n goes to infinity of 1 plus 1 over n all raised to the nth power. That's the normal definition of the number e. And you can try, go ahead and put your phone number, take this expression and put your phone number in for e. I'm not going to use my phone number because obviously I don't need everybody in the world to know my cell phone number, but 1 plus, right, in parentheses, 1 plus 1 divided by 99999, close parentheses, all raised to the, let me see, how many 9s did I use there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2.71828, blah, 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 right? This number, very, very close to e. So as n gets bigger and bigger and bigger, 1 plus 1 over n, all raised to the nth power becomes the number e. This is the thing that comes from compound interest, right? That's how you're supposed to learn this. I don't know if your college algebra or pre-calculus teachers did a good job. Many do not at this particular thing, but this comes from repeated application of the compound interest formula with the nominal interest rate set at 1. So what we want to do is show that this definition gives us this limit being 1. And the way we're going to do this is in lim h, even better actually, in the definition above, let n equal 1 over h. So what I'm about to do, you're not responsible for on a test, just to be clear. Right? What you're responsible for is this fact. The derivative of e to the x is e to the x. So I'm going to do this quickly. If n is 1 over h, then as n goes to infinity, we must have h going to 0. For this to go to positive infinity, h needs to go to 0. Right? Or the other way around. If h is going to 0, then this must go to infinity. So if e is by definition equal to the limit as n goes to infinity of 1 plus 1 over n all to the n, this is the same as saying e is equal to the limit as h goes to 0 of, everywhere there's an n, I write 1 over h instead, right? Everywhere there's a, n is 1 over h. So that's 1 plus 1 over n is h, right? 1 over h. And then n is 1 over h. Simplifying, this says e is equal to the limit as h goes to 0 of 1 plus, well, 1 divided by 1 over h, that's h. So this is 1 plus h, all raised to the power of 1 over h. Which means for h's which are very, very close to 0, we have e is very, very close to 1 plus h raised to the 1 over h. Raise both sides to the h power. You get e to the h is equal to 1 plus h. You can see where this is going. Subtract 1 from both sides. E to the h minus 1 is equal to h. Remember, this is all assuming h is very, very small, very close to 0. Now divide both sides by h. E to the h minus 1 over h equal to 1. And I guess these should all be shaky equal signs, I guess, approximately equal to. And this is all assuming that h is very, very close to 0, i.e., the limit as h goes to 0, e to the h minus 1 over h is equal to 1. And that completes the proof. So
On the test, are we going to have to prove any of this?
No. Nope. But I cannot, in good faith, as a calculus teacher, tell you that the derivative of e to the x is e to the x without showing you why. And the book's argument is crap. So here's the real reason, right? So the book's argument, it's not all crap, right? It's fine up to this point. But then they just say that this number is defined to be 1. That's crap. So what we're doing in the proof here is just really showing that if you take the normal definition of e, then you can get that fact from it. Right, that's all. So it is true that e to the h minus 1 all divided by h is very, very close to 1 if h is very, very close to 0, which is the same thing as saying that the limit of e to the h minus 1 over h as h goes to 0 is 1. So it's a true statement. The connection between the definition that Stewart uses and the definition that everybody else in the world uses is this right here. So if h is the number in the Stewart definition and n is the number in the definition everybody else uses, then replacing n by 1 over h and observing that n going to infinity is the same as h going to 0 gives you the result. All right. The meat and potatoes here is practice with the rules. So let's practice with the rule. All right, if f of x is this bizarre cattywampus sum of power functions and exponentials, can we find f prime? Well, I have a rule that says I'm allowed to differentiate each of these things on their own because they're just being added and subtracted. And I have a rule that tells me how to differentiate powers of x, and a rule that tells me how to differentiate e to the x. So yes, f prime of x is what we get when we differentiate this thing. And I'm going to write this line just with some stuff simplified here. That's 2x to the 1/2, right? The square root of x, plus x to the -3 minus 4 times e to the x. And now I differentiate each one of those pieces individually using the appropriate rule. The first two pieces get the power rule because they are power functions. So this is 2 times 1/2 times x to the 1/2 minus 1 is -1/2, plus, bring down the power, -3, x to the -3 minus 1 is -4. Minus, I've got 4 e to the x that I need to differentiate. The 4 is a constant multiple, so it just comes along for the ride, and the derivative of e to the x is e to the x. And we can simplify a little bit. The 2 and the 1/2 cancel. X to the -1/2 is 1 over the square root of x, plus -3 x to the -4, that's -3 over x to the 4, and then -4 e to the x is chilling. Any questions on this guy? Okay. Besides new differentiation rules, there's one bit of terminology that shows up in this homework set for the first time. And that is the concept of a normal line. So let's find the tangent line and the normal line to the function 2x plus e to the x at x equals 1. We know what the tangent line is. Has anybody heard the term normal line or encountered the word normal in mathematics anywhere? So if you've taken physics, this is pretty common. Cameron's comment in the chat is correct. It will be the line whose slope is the negative reciprocal of the slope of the tangent. What do if I have two negative reciprocal slopes, what's the relationship between those lines?
They're perpendicular.
Very good, they're perpendicular. This is an important concept in physics. The tangent line, you know, is the line that like just kisses the graph, right? It's the line that tells you the slope of the graph right at that point, because curvy things have slopes that are constantly changing. So here's the tangent. The normal line is the line that passes through that same point, but is perpendicular to the tangent line. So the purple here is the normal line, and the black straight line here is the tangent line. You might ask, why do I give a shit about normal lines? Well, for one, when you stand up on a surface, the force that keeps you from falling through that surface, the force you feel against your feet, is called the normal force, and it points directly out from that surface. So in physics, big important concept, right? You know that F equals ma, the fact that we are not currently accelerating towards the center of the Earth means the Earth must be exhibiting some force outward on us to keep us from falling in, because gravitational acceleration points down. We would normally accelerate down, but we're not. We're sitting our butts in the chair, which means the chair is exerting a normal force upward on our butt. Don't think about the vector too hard. It's not a pleasant picture. In any case, the normal line is like the tangent line, except it's perpendicular, right? Same thing. So it's going to be a point slope thing. You find the point, and then you take the slope of the tangent line and you take its negative reciprocal. That's how you find the slope of a line that is perpendicular to a given line. Okay, so the other thing to remember here, I guess, is two lines are perpendicular if m1 is the negative of 1 over m2. All right, the slopes have to be negative reciprocals. So a line of slope 2 is perpendicular to a line of slope negative 1/2. Means they meet at a 90-degree angle. All right. So if I want to find the tangent line or the normal line, both of those require knowing the slope of the tangent line, which I get from the derivative. So first thing we do is differentiate. No more big limit here, thank goodness. F primed, I just get from the power rule here for 2x. So that's 2x to the 1. So his derivative is 2 times 1x to the 0, which is just 2. Plus the derivative of e to the x is e to the x. So the slope of the tangent line at x equals 1 is f primed of 1, which is 2 plus e to the 1, or just 2 to the e. And then our point of tangency, that's always a comma f of a. Here it'd be 1 comma f of 1. So if you plug 1 into the original function, what do you get? Well, you get 2 times 1, which is 2, plus e to the 1. Oh, so that's also 2 plus, sorry, shit. The x value is 1, and the y value is 2 plus e. So your point of tangency is 1 comma 2 plus e. Therefore, the tangent line is y minus 2 plus e equals the slope of the tangent, which is also 2 plus e, times x minus 1. There's your tangent line. The normal line is going to use the same point. There's a symbol for this, m perp. The upside down capital T here is the symbol for perp, or perpendicular. This would be negative 1 over m tan, right? The negative reciprocal of the slope of the tangent line, because my normal line is perpendicular to the tangent line. So that's negative 1 over 2 plus e. Therefore, the normal line, we use the same point, right? Still 1 comma f of 1. The point of tangency is the same as the point of normalcy, if you want to call it that. The normal line would be y minus y0, y minus 2 plus e equals his slope, which is -1/2 plus e times x minus x0, which is x minus 1. So that is your normal line. Okay. Normals will be important in physics, also important in Calc 3 when you're talking about like a surface, a 3D object, and you want to find a tangent to that. The tangent object there will be a tangent plane, and the best way to determine that is to determine the normal vector that points straight out of your surface. So there will be applications to this concept of a normal line, but not in Calc 1 or Calc 2. But it shows up here. Okay. So we're starting to feel pretty ballsy. We can differentiate polynomials, power functions of any flavor. We can differentiate certain ratios of power functions and polynomials, right? Where, like we did last time at the very end, where you split it up over the bottom, stuff like x squared plus 2x over the square root of x. You can split that up, right, as power functions differentiate. You now can throw exponentials into that mix, and it starts to feel like we can differentiate a lot of stuff. But how would you differentiate something like x e to the x? And I'll tell you, the derivative of this function is not just e to the x. You cannot just differentiate the x to 1 and differentiate e to the x to e to the x and call it a day. Totally reasonable thought to have, but it doesn't work. In general, if you want to differentiate a product of two functions, if you want to prime something that looks like f of x times g of x, this is not f primed times g primed. So the derivative of x e to the x is not 1 e to the x. That doesn't work. There's a good reason for this. You can think about it geometrically, but the result, I should just share with you, it's called the product rule. This is, I'll write it in the prime notation. If you have a product of two functions like f of x times g of x that you wish to differentiate, you differentiate them one at a time, leaving the other guy alone. So this is f prime times g plus f times g primed. So if I wanted to differentiate I have to think of each of these as being their own little function. Now don't confuse yourself with the labels. I'm using f and g for the two functions in the product here, and I'm using f for the overall function here. but this is like my little f, and this is like my little g. So this would be the derivative of the first function with the second function left alone, plus the first function times the derivative of the second function. And this way of schematically writing things out with the primes, you really want to do this, right? These problems will get big, and if you try to do it all at once, you'll make mistakes. So please, as you work out these big product rule and quotient rule problems, a step like this will make your life so much better, I promise. Also, you can check your work with it. So applying the product rule, we get derivative of the first times the second plus the first times the derivative of the second. And now we actually take the little derivatives. The derivative of x is 1, so this is 1 times e to the x plus x times the derivative of e to the x is e to the x. So in other words, the derivative of x e to the x is e to the x plus x e to the x. There are places where you can use the product rule, but you don't need to. And it's good to identify those. It's good to be able to see those when they crop up. Some of your homework asks you to solve problems 2 different ways.
I have a quick question.
Yes, please.
When, like in an answer like this, would you also accept if we went a step further and took the e to the x out and then made it times 1 plus x, or is that just not
Absolutely.
necessary?
No, that's very nice. Yeah, I like that. 1 plus x times e to the x like this.
Yes.
Yep.
And then also the problem back, I'm sorry,
No,
when you put in the homework, it allowed us to do like the 1 over square root of x. You put it back to that form where the homework was allowing us to do like x to the negative half. Which
Either one
way
would-
is it proper?
either one would be fine there as well. So what did we have here?
I'm sorry, it's far back.
No, that's okay. I just have to find the page. Here.
There it is.
So if you wanted to leave this as x to the negative 1/2 or this as x to the negative 4, that would be fine. Either one.
Okay.
This or this, yeah. If a problem requires a certain kind of simplification, I'll say so in the statement of the problem.
Okay,
There
thank
are a
you.
lot of instances, and I'm glad you mentioned this, there are a lot of instances where having the derivative factored is really nice. Because I could ask, when is the tangent line horizontal, right? I could ask questions like that about the tangent line. So we could go on to say, for what x values is the tangent line to f of x equals x e to the x horizontal. Now, this is leaning more towards the application of derivatives stuff, which we will certainly get deep into, but that's exam 2. But a question like this is pretty fair game because it's more about just interpreting what the derivative means. So we know that the slope of the tangent line at any x value is equal to the derivative of that function at that x value. And in the part above, we calculated the derivative of this function to be 1 plus x in parentheses times e to the x. So to answer the second question here, for what values of x is the tangent line to x e to the x horizontal, I need to know when this thing, the derivative, the slope of the tangent line, yields a horizontal line. So what is the slope of a horizontal line? what kind of lines have, I should say, what, yeah, horizontal lines have what for their slope?
Zero?
Yeah, right. A horizontal line is a line of slope 0. So this would mean that the slope of the tangent must be 0, right? In order to have a horizontal tangent line, the slope of that tangent line, m tan, must be 0, which means that this apparatus, 1 plus x times e to the x, must be equal to 0. So having the derivative in factored form is really nice, because, you know, solving equations like some shit equals 0, you step 0 is to factor everything. E to the x is never 0, right? We have here a product of two functions equals 0. By the 0 factor rule, this means either 1 plus x equals 0 or e to the x equals 0. If 1 plus x is 0, then x is -1. E to the x is never 0. This never happens. So for what x values is the tangent line to that graph horizontal? -1. And if you look at the graph of this function, I'll show you in Desmos really quick. I'll just hold here for a second, make sure everybody has these lines down. Okay, swapping to Desmos in 5. Here she is. So here's the graph of x e to the x. You see it's got some curvy stuff going on. Right here at -1, that's where I have a horizontal tangent line. If you look at the tangent line at that point.
I'm sorry, we can't see it.
Oh, really? Okay, sorry. Let's share full screen. There you go. Is that better?
Yes, thank you.
All right. Yeah, no problem. So red curve here, x e to the x, it's kind of curvy, right? It's like going down, and then it like switches its curvature a little bit, and then it's coming up. Right here at -1 is a point where the tangent line would be horizontal, right? It'd be -1 over e. Right, if you just look at this little tangent segment down here, that is horizontal. And that's the only x value where this curve would have a horizontal tangent. And that's precisely what we found, is that x equals -1, we have that. So finding the location of horizontal tangent lines is going to be a very big deal down the road. And it is something that I could ask you to do on the first test if you're working with a derivative that's, you know, nice enough. This is a great example of an exam caliber problem. Find this derivative, tell me where the tangents are horizontal. So factored form of derivative is fine, and sometimes necessary. The product rule is useful, but don't overuse it. Do we need the product rule to differentiate? Let's look at some examples. About f of x equals x times the square root of x. G of x equals x plus x squared times 1 minus 2x. So do we need the product rule to differentiate either of those functions? They both look like products, right? Both of these are like one function times another function, or one function times another function. And in both cases, you could use the product rule. But in neither case must you use the product rule. And I would argue that in both cases, you're wasting time if you do. So the answer here is no to both. F of x is x times x to the 1/2. Right? The square root of x is x to the 1/2. And if you just use your basic algebra rules, x to the 1 times x to the 1/2 is x to the 3/2. So f primed can be computed using the power rule as 3/2 times x to the 3/2 minus 1 is 1/2. Totally valid and way faster. That's part A. Part B, g of x, yeah, sure, it's a product. But it doesn't have to be a product because I can multiply it out. If I FOIL this out, that's my first is x times 1. My outers are minus 2x squared. My inners are plus 1x squared. And my last are minus 2x cubed. And you could differentiate from here, but you can save yourself even more time by combining these like terms. So minus 2x squared plus 1x squared. Let's put this in the standard order with the large term at the front. So minus 2x cubed. And then I've got negative 2x squared plus 1x squared. That's minus 1x squared. And then I've got an x over here. So plus x. So g primed would again follow from the power rule. Negative 2 times 3 is negative 6x squared minus 2x. And then the derivative of x is 1. So no need for the product rule here in either of these. Although you could use it on either if you wanted. It's just, should you? And I would say, no, it's a waste of time. So what I'd like to look at next is a problem that is a little bit more abstract in nature. I'm going to do 2 of these. How am I doing on time? 3:04. We got to move a little quick. Okay, actually, I have another theorem to show you. So let me get this out of the way first. This is called the quotient rule. Some things, just like some things are products and you cannot help it, like x times e to the x or x squared times e to the x. No expanding that out. Some things are quotients and you can't help it. So what the quotient rule says is if you have a ratio that you want to differentiate, just like with derivatives of products, you cannot differentiate each piece on its own and multiply them. With the derivative of a ratio, you cannot just say it's f prime over g prime. That's not correct. This one is kind of messy. it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all divided by the square of the bottom function. Most Calc 1 students do not like the quotient rule, and I don't blame them because it's kind of messy. There is a mnemonic to help for this. You sing it in your head like that song from Snow White, hi ho, it's that shit. Low d high minus high d low over low low, which means low d high, bottom times the derivative of the top, minus high d low, top times the derivative of the bottom, over low low, the bottom squared, or the bottom times itself. Like the product rule, there are cases where you cannot escape this. Let's do x squared over e to the x. So here, you can think of little f as being x squared and little g as being e to the x. The proofs of the product and quotient rules are not enlightening. I'll just say it, right? It's all symbol juggling. You just mash around the algebra until it falls out. So I'm not showing you the proofs of these because they don't teach you anything. But using them, we need to be able to do. So I'll have the bottom times the derivative of the top, or g times f prime, minus the top times the derivative of the bottom, all over the bottom squared. So f primed, if you're wanting to plug into that formula up there, f primed is 2x and g primed is e to the x. I'll tell you the way I do it. I don't plug into that formula. I write it out schematically using that mnemonic. So this is low d high, bottom times the derivative of the top. So I'd write it as e to the x times x squared primed minus high d low, that's the top, times the derivative of the bottom, so x squared times e to the x primed over low low, or the bottom squared, e to the x all squared. And now in the second step, so first I like to write it out schematically like this. It lets me get something on the page that I know is correct, from which I can continue working without trying to do too much at once. Then I go ahead and compute the individual derivatives. So that's e to the x times derivative of x squared is 2x minus x squared times the derivative of e to the x is e to the x, all divided by e to the x all squared, which is e to the 2x. And we can factor out an e to the x, as in that previous example. And what's left upstairs is 2x minus x squared. Downstairs is e to the 2x. You can cancel the e to the x into the e to the 2x. Remember, e to the 2x is e to the x times e to the x. So this is 2x minus x squared over e to the x. And you could also factor the rest of the top. That's x times 2 minus x. But I would accept any of these as an answer on a test. If all I said is differentiate this thing, any of these 3 lines would be an acceptable answer. If you had to go on to do stuff with that derivative, boy, you really want this bottom one. But if you're just worried about finding the derivative, any of those 3 are fine. The algebra rule here, in case anybody's wondering, there's one kind of sneaky algebra rule that's used. E to the x all squared, like a to the b all to the c, is the same as a to the b times c. So when I write e to the x all squared as e to the 2x, this is the rule I'm using. And then canceling the e to the x with the e to the 2x, I'm using a similar rule. Right? You could, if you want, you could just think of this as e to the x times e to the x, and you cancel one of them. Okay, but these algebra steps are they're the big challenge in Calc 1, right? It's getting to a place where you can manipulate the expressions comfortably and get to a point where you can use them to do other stuff. If I was going to go on to try and find horizontal tangents or something here, I would factor the top as x times 2 minus x, and then leave the bottom as e to the x. Before I let you go, there's one other thing I want to look at, and that is problems where the quotient rule appears to be necessary but isn't. We saw one of these the other day. So is the quotient rule needed? I want to calculate that. Or how about that? So thoughts on the first one?
Shouldn't you just factor and then cancel out the top and bottom x?
Very good. There's a factor of x common to the top and bottom. Let me make it worse. What about now?
Can't you multiply by x to the negative 1/2?
Isabella's suggestion is a valid one. That's one way to think of this. I'll tell you, the way I think of it is slightly different, but it's the same thing. Before I do any calculus, I could write this as x cubed minus 2x squared all times x to the negative 1/2, all still inside this derivative, then distribute the x to the negative 1/2. The result is going to be the same thing as if you, I like to think of it as splitting up the fraction. So the algebra rule, and again, very useful. You use this the other way all the time. When you add fractions, you have to have a common denominator, then you just add the tops, right? Well, shit, if you have a fraction where the top has multiple parts and the bottom has one part, you can split it up also. So root x is x to the 1/2. And then I just write this over that minus this over that. You can split fractions up across their numerator, and the result is the same thing you would get from what Isabella said. This is now x cubed times x to the negative 1/2. This is now 2x squared times x to the negative 1/2. So be still doing algebra, no calculus yet. X cubed times x to the negative 1/2, or x to the 3 minus 1/2 is x to the 2.5, or x to the 5/2, minus 2 times x to the 2 times x to the negative 1/2, or x to the 2 minus 1/2 is x to the 1.5, or 3/2. Now you take your derivative using the power rule. This is 5/2. X to the 5/2 minus 1 is 3/2, minus 2 times 3/2. X to the 3/2 minus 1 is 1/2. You can cancel the 2's. You get 5/2 x to the 3/2 minus 3 x to the 1/2. No quotient rule. And believe me, you want to do this. You don't want to do the quotient rule on this. It's worse. So always simplify using algebra first if you can. What about part B? Is there any?
Factor out the top.
Yeah, if I factor the top here, he has within him a factor of x minus 2 that will cancel. That numerator is x plus 3 times x minus 2. And the bottom, x minus 2, is just x minus 2 times 1. So when you cancel, we're really just differentiating x plus 3. And that is, again, a power rule derivative. That's 1. Can you imagine going through all the bullshit with the quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared, to find at the end of the day that the goddamn thing comes out to 1? I don't know about you, I'd be a little annoyed. So wherever possible, simplify the object you're working with using algebra before applying any calculus rules, especially the quotient rule, because it's a messy thing. It's a messy thing, and there's no getting around the quotient rule being messy, but there is getting around the quotient rule entirely if you can get rid of the quotient. So try to do that. Try to do that. Other examples like this, I won't go through it. If I asked you to differentiate, actually, you don't have that tool yet. No, I'll hold off on that. We'll just leave it at this, right? Simplify algebraically if you can first. All right, always. That's it for me today. Your homework set has plenty of things to play with involving polynomials, power functions, and exponentials. It also has a lot of stuff to do with the product and quotient rules. So practice those things before we meet on Friday. On Friday, we're going to do a few things. There are some problems in your homework where you're given like graphs instead of algebraic representations of functions, and you're asked to come up with products and quotients and derivatives of those things. If you just follow the rules and look at the graphs and think about what the derivative of that graph should be at the points in question, you can get there. I do want to work one of those for you. So if you're hung up on those at the moment, don't panic. I'll do one on Friday. The other thing we're going to do on Friday is differentiate the trig functions. We haven't done that yet. Sine, cosine, tangent, secant, cosecant, cotangent. We're going to find the derivatives of all of those. And baked into that are two kind of challenging limits. Just like that e to the h minus 1 over h limit today, there are some wonky, difficult limits involving trig functions that we're going to have to wrestle with there. I'll try to make it tractable. I'll try to do it in a way that doesn't waste a lot of your time because it's not something you'll be tested on. But like today, it's an important thing. And if I don't show you, I'm being bad calc teacher. So for me to avoid being bad calc teacher, but also to avoid you feeling grumpy about the limits feeling weird, maybe take a look at Where is it in here? So proofs of product and quotient rule can be found here. This is the limit that I'm thinking of as being a little tricky. No, it's over here. All right. Proofs of product and quotient rule, if you want them, they are here. They are not conceptually important, so I don't care if you study those or not, just learn the rules. This one, this is a limit we're going to have to deal with tomorrow, and it's actually kind of hard. So the argument I will use is going to be a geometry argument. It's actually this argument. This is my favorite. You might want to study this a little bit before class on Friday because it will help you understand what we're doing. We're going to use inequalities that come from thinking about areas here. Like the big triangle area on the outside is bigger than the blue shaded area, which is bigger than the little right triangle area on the inside. And those turn out to be this. And then we're going to use the squeeze theorem. So we're going to be making use of some kind of challenging geometry, inequalities, and the squeeze theorem on Friday. It would be wise to at least glance at this before class then, so you're not totally lost there. But that's it. So work hard, focus primarily on the homework. If you have time before class on Friday, take a look at this link. It is again under chapter 3 resources in the modules. That's it from me. If there's anything I can do to help you guys, send me a Canvas message, come by office hours, Desmos, not Desmos, bring in Discord. You know the drill at this point. I'll see you on Friday. We're going to set up the exam on Friday as well. Friday, we're going to set the date for exam 1, which is coming. It'll probably be late next week. So that's it. Take care again. I'll see you on Friday.
Thank you, Professor.